Next we come to stereoisomerism. So we have already done our normal structural isomerism and now we come to stereoisomerism. So I had already explained to you how structural isomerism and stereoisomerism are different from each other. Right? In structural isomerism, connectivity changes. In stereoisomerism, connectivity remains the same, but what changes is the orientation of the ligands in three-dimensional space. So, and you know that stereoisomerism is also of two types. We have geometrical isomerism and we have optical isomerism. So, let us learn more about that now. So, geometrical isomerism, it arises in heteroleptic complexes due to ligands occupying different positions around the central atom. First of all, heteroleptic complexes. So, coordination complexes can be said to be of two types, homoleptic and heteroleptic. Homoleptic coordination complexes are those in which all of the ligands present within the coordination pair are the same. If you talk about like CrNH3 whole 6 3 positive, that's a homoleptic complex. And this is it's a homoleptic, it's not Y, it's E, homoleptic complex, and if all of the ligands present within the coordination pair are not the same, these are your heteroleptic complexes. So, geometrical isomerism cannot be shown by complexes which are homoleptic, they can only be shown by complexes which are heteroleptic. Like if we talk about a complex M A2 B2, okay, it's a square planar complex, coordination is 4. Coordination number is 4. So, what can happen, either the A can be present opposite to A and the B can be present opposite to B, or what can happen is the A can be present opposite to B and the B can be present opposite to A. So, this is what geometrical isomerism is. This is said to be the transform. In transform, the same ligands are present at an angle of 180 degree to each other. You can see this is an angle of 180 degree. And this is known as the cis form. In the cis form, the same ligands are present at an angle of 90 degree to each other. Here the angle between A and A is 90 degree and the angle between B and B is also 90 degree. So, geometrical isomerism has two forms. It is transform and it has cis form. So, as I had already said, geometrical isomerism has transform and it has cis form. So, cis form arises when there are two different transform and cis form, both of them they arise when there are two different types of ligands present, like M A2 B2. Okay. If there are two different types of ligands present, but one of the ligand, like let's say M, it's MA3B. Okay. In this type of complex, cis trans isomerism cannot be predicted, because if I write it like this, then I can say, okay, first of all, A is opposite to A. But then the other option, I am left with no choice but to write A opposite to B. Okay, I can say A is trans to A. Here the angle is 180 degree, but here the angle is also 90 degree. So, this is neither a transform nor a cis form. So, transform and cis form is applicable only for them. We can say that A here is trans to B and this A is trans to A. Okay. So, when I say something is trans to something, I mean that there is a angle of 180 degree between those two ligands, and if I say something is cis to something, that is if A ligand is cis to A, I mean that between A and A ligands there is an angle of 90 degree. Now we come to optical isomerism. So, optical isomerism are substances, okay, first of all, substances which rotate the plane polarized light are said to be optically active. Now, what is plane polarized light? Normal light has wave in all the directions, right? And what is plane polarized light? Plane polarized light is the light which has all the waves moving parallelly only in one direction. So all those complexes which rotate the direction of this plane polarized light are said to be optically active. Like if you pass the plane polarized light through a complex and it rotates the plane polarized light towards this side, that complex will be optically active. If you pass the plane polarized light through a complex and the plane polarized light is rotated towards this side, then also that complex is said to be optically active. So this is the main criteria for classifying something as optically active. That is, it should rotate the plane polarized light. So next, the isomers which rotate the plane polarized light to the same extent but in opposite direction are called enantiomers. Let's say I have a compound or I have a complex, okay, and that complex has two isomers. I take one of that isomer and pass plane polarized light through that isomer. Plane polarized light was originally in this direction. Now what it has done, it has rotated the plane polarized light towards this direction by an angle of, let's say, 60 degree. Okay. Now if the other isomer, there is the second isomer also. Now if the second isomer rotates the plane polarized light towards the opposite direction, also by an angle of 60 degree, then the first and the second isomer, they are called enantiomers.